Alright, so section 3.10, derivatives of inverse trigonometric functions. So here I have theorem 3.22 from the book, which lists all of the derivatives of the 6 main trig functions, of the inverse trig functions. So you can see them here. A couple of them are derived in your book. I wanted to derive one here. I wanted to derive the derivative of inverse cosine. So this derivation is really similar to the derivation of the derivative of inverse sine. So the method is that we let y equal cosine inverse. And then we take the cosine of both sides, so we get that x equals the cosine of y. And then we use implicit differentiation to find dy dx. So implicit differentiation, we would have minus sine of y dy dx is equal to 1. So we're taking the derivative with respect to x here. Y depends implicitly on x, which is why we have the dy dx, and it's why we take the derivative of x as usual. Okay, so now we solve for dy dx, and we have that dy dx is equal to minus 1 over sine of y. But, our original derivative is with respect to x, so we want our answer to be in terms of x's. So I go back to the idea of a right triangle. I have this kind of relationship between x and y, that cosine of y is equal to x. So if I call this little angle here y, if the cosine of y is x, then that means this side is x, the hypotenuse is 1, and using the Pythagorean theorem, we see that the third side would have to be radical 1 minus x squared. Okay, so that means that the sine of y is opposite over hypotenuse, or in other words, root 1 minus x squared over 1. So plugging that into our derivative, our dy dx, we get minus 1 over root 1 minus x squared, which is exactly what we wanted. Okay? So we just proved this guy right here. Okay, and your book shows you the derivative of sine inverse and the derivative of tangent inverse, so I'd encourage you to work through the other ones. At the end of the day, you should definitely know these derivatives. Alright, let's see an example. So here we're going to evaluate the derivative of sine of tangent inverse of the natural log of x. So we'll have to use the chain rule here. So last week we learned all about the chain rule. Now we are combining the chain rule with derivatives of inverse trig functions. So f prime of x is going to equal the derivative of the outermost function, which is sine. So derivative of sine is cosine. So we have the cosine of our original argument times the derivative of what's inside the argument of sine. So we're multiplying it by the derivative of tangent inverse of the natural log of x. Now the derivative of tangent inverse is 1 over 1 plus x squared. Okay, so that's one of our identities, or main derivatives here. Okay, so the argument in this equation is an x, so the derivative of tan inverse of x is 1 over 1 plus x squared. So now we have a slightly more difficult or complicated argument of ln of x. So we're going to be multiplying by 1 over 1 plus the natural log of x squared times the derivative of the natural log of x, which is 1 over x. Okay, so all in all, if I clean things up a little bit, simplify, I'm just going to rearrange essentially. We have 1 over x times the quantity, 1 plus the natural log of x, the quantity squared, times this cosine of tangent inverse of the natural log of x. And that is our derivative. Okay, so we're combining a lot of ideas here. We're combining the chain rule with derivatives of inverse trig functions, with derivatives of natural logs. Okay, so these are all very recent concepts here. Okay, next example. I'm going to find the derivative of f of t, where f of t equals the cosine inverse of t, the quantity squared. So again, we are going to apply the chain rule. F prime of t is equal to 2 times cosine inverse of t times the derivative of cosine inverse of t, which is minus 1 over root 1 minus t squared. And simplifying that a little bit, we get minus 2 over root 1 minus t squared times cosine inverse of t. Okay. So that is, a couple different examples of inverse trig functions. The last example I wanted to talk about involved finding the derivative of an inverse at a specific point where you're given the function, not the inverse function. And it turns out we have a nice little formula for this. We have a theorem 3.23. It's the derivative of an inverse function where you don't have to actually find what the inverse function's equation is. So this formula tells us that f inverse prime of y naught is equal to 1 over f prime of x naught. Okay, so let's do this derivative with that idea. So we want to find the derivative of the inverse of f of x when f of x equals minus 5x plus 4 at the point minus 1, 1. So our x naught, y naught is equal to the point minus 1, 1. So that means that x naught is minus 1, y naught is 1, or in other words, f of minus 1 equals 1. So there's just two different ways to write the same thing there. Plugging that into the nice formula that was given, we would have f inverse prime of 1 is equal to 1 over f prime of minus 1. And so all we really need to calculate here is f prime of x and evaluate that at negative 1. But f prime of x, f of x was originally minus 5x plus 4, so f prime is minus 5. It's a constant. So f prime at negative 1 is still minus 5. So we would have f inverse prime of 1 is equal to negative 1/5. And we're done. Okay, so, if there's a inverse function that's really difficult to find, this formula can save you some time. Alright, well that's all I have for this section. I hope you enjoyed it.